the goal is Bézout lemma or theorem or identity. So we have n, and n is an integer greater than or equal to 2, strictly positive integers, x1, x2, xn. There exist integers a1, a2, an, such that the integer combination of the x's, which is in this form, is exactly equal to the greatest common divisor of the x's. We are interested in another result, which is if the x's are coprime, if the GCD is equal to 1, there exists y tilde such that for every positive integer y greater than or equal to y tilde, we have that y is a strictly positive integer combination of the x's. Y is equal to summation k from 1 to n, ak xk, but ak is strictly greater than or equal to 1. It's an integer that is strictly greater than or equal to 1. Let's start by defining set big S, which is a set that includes every possible integer combination of the x's. Note that if there is an element of S that is, let's say, B, so this means that B can be written as an integer combination of the x's. Let's say that it is a1 bar x1 plus a2 bar x2 and so on. Then any integer multiple of B is in set S, because if you take B and multiply by an integer V, then here we will have V times a1 bar, and this is an integer, all times x1. And then here we will have V times a2 bar, and V is an integer, a2 bar is an integer, the product is an integer, and this is multiplied by x2 and so on. So VB is an integer combination of the x's. So by definition, it is an element of set big S. If there is an element B in S, then every integer multiple of B is also in the set S. Now suppose that you have another element of S, which is C, and it is equal to a1 tilde x1 plus a2 tilde x2 and so on. Now what about B plus C? B plus C, there will be a term in which x1 is multiplied by a1 bar plus a1 tilde. a1 bar is an integer, a1 tilde is an integer, their sum is an integer. So we have an integer times x1. And then x2 will be multiplied by a2 bar plus a2 tilde, and this again is an integer, and so forth. So the sum is an integer combination of the x's. So by definition, it's an element of S. So the summary is that any element in S will basically, if there is an element in S, then all the integer multiples of that integer will also be in the set S. And if there are two elements of S, these B and C, there are integers and they are in S, then their sum will also be in S. Now, let's basically define eta to be the smallest strictly positive integer in S. So S is a set with integers, and let's basically search for the smallest positive integer that is in S, and this will be called eta. Now, this eta exists by the well ordering principle. So the well ordering principle just says that the set of positive integers is well ordered, which means that each and every non-empty subset of the set of positive integers, it has a smallest or least element. So this, here will be called eta. And let's examine the division of x1. So this is the first guy here, x1 by eta. So there will be a quotient, so q, which is equal to the floor of x1 over eta. That's the quotient. And then there is a remainder, and the remainder is r. And r is 0 or 1 or 2, and its maximum possible value is eta minus 1. So this is basically the division algorithm. It tells you that you can write down x1 as a quotient q, an integer times eta plus a remainder, and this remainder is a range. It's an integer value that ranges from 0 to eta minus 1. Now put r on one side. Okay, so here is r, and then on the other side we have x1. Let's write x1 as 1 times x1, or just write it as x1. And then when we move this to the other side, we will have minus q times eta. Now x1 is an element of big S, because big S contains all integer combinations of the x's. And so if you choose a1 to be 1 and all the other a's to be equal to 0, then x1 will be, then this integer combination will be x1, and so it will be an element of S. So basically all the x's are in this set S and all their integer multiples and so forth. So x1 is in S. Now eta by definition is in S because it is the smallest strictly positive integer that is in S. So eta is also in S. Minus q times eta is an integer multiple of eta, and we basically we have seen that if there is an element b in S, then all its integer multiples will also be in S. So if eta is in S by definition, then all its integer multiples will be in S. So this term will be in S. And we have also seen that the sum of two elements in S will also be an element of S. So the conclusion is that if R can be written in this form, then it must be the case that R is in S. R is in S. So R can be 0 or 1 or 2 and so on. The claim is that R cannot be a positive integer. It must exactly be equal to 0. Because if R is a positive integer, the range of values that it can take, those values are all less than eta. So if R is basically one of those positive values and R is in the set S, then this will contradict the definition of eta. Eta by definition, it is the smallest positive integer in set S. So if there is an R in S and R is, for example, eta minus 1, well, that is less than eta. And so we here contradict the very definition of eta. So R cannot be a positive integer. So the only remaining possibility is that R is exactly equal to 0, which means that if we divide x1 by eta, the remainder is 0. So this means that x1 is a multiple of eta, or x1 is divisible by eta. Or to say it in another way, eta is a divisor. It's a factor of x1. Now this argument here can be repeated using x2 and x3 all the way to xn. And in every case, the conclusion will be that eta is a divisor of x2 and x3 all the way to xn. So the conclusion is that eta is a common factor of the x's. So the set S, it contains a smallest strictly positive integer. This eta must be a common factor of the x's. Because eta is in the set S, then we are able to express eta as an integer combination of the x's by definition. So we can always find integers u1, u2 to un such that u1 x1 plus u2 x2 to un xn is equal to this eta, which we have discovered to be a common factor of x1, x2 to xn. Okay, now suppose that the x's as positive integers, they have another positive common factor, let's call it gamma. Because x1 has a factor gamma, then I can write down x1 as q1 gamma. Because x2 has a factor gamma, then I can write down x2 as q2, an integer times gamma, and so on. And so eta is equal to gamma. So eta is a common factor of the x's. Gamma is some common factor of the x's. Both gamma and eta are positive, and now they are related by this expression. Eta is equal to gamma, and then there is an integer here, which is given by this. Note that eta is positive, gamma is positive, so this bracket here must be positive. And positive integers, they have a minimum value of 1. So this quantity that we have on the right-hand side is greater than or equal to gamma. In other words, that this eta, which lives in set S, must be greater than or equal to any common factor of the x's. And so eta is not just a common factor. Eta is indeed the greatest common factor, or the greatest common divisor of the x's. Okay, so this is the proof that the greatest common divisor of the x's can be written as an integer combination of the x's. So we started by defining set big S as the set containing all possible integer combinations of the x's. We discovered that the minimum strictly positive integer in set S is the GCD of the x's. And because the GCD is in set S, it is indeed the smallest strictly positive integer in set S, then by definition, it can be written as an integer combination of the x's. Okay, so eta can be written as this summation here, where the u's are integers. Okay, so this is the conclusion. Before proceeding, note that one of these u's must be non-positive. One of those u's must be non-positive. So suppose that all the u's are strictly positive. Then from this expression, eta, which is equal to summation k from 1 to n uk xk, is greater than or equal to the summation of the x's. You know, those are, the x's are distinct positive integers, but then eta is greater than or equal to the sum, while eta is actually the GCD of the x's. Okay, so it is less than or equal to each one of them. Okay, and so it must be the case that at least one of the u's is non-positive. Now let's move to the second part. Take a positive integer L, and now our focus will be the case in which the x's are a coprime. So the GCD is equal to 1. Note that when the GCD is equal to 1, then the set big S that we defined here, it contains the GCD. And because it contains the GCD, it contains all the integer multiples of the GCD. So if S contains the integer 1, then it contains all integer multiples of 1. So in this particular case in which the x's are relatively prime or coprime, actually the set big S will be the set of integers. Which means that if those guys are coprime or relatively prime, then any integer can be expressed as an integer combination of those x's. Now let's go back here. Let's examine, the division of L by the summation of the x's. Okay, so there will be a quotient which is J, which is the floor of L over the sum of the x's. Okay, and then there will be a remainder, and the remainder, again by the division algorithm, the remainder is basically an element in this set, either 0 or 1, all the way to the summation minus 1. Now, because the GCD is 1, then take this D here. So we have J and then the sum plus D. I will put here the GCD because the GCD is equal to 1. And the GCD can be written as this integer combination of the x's. Now combine the two sums. So L is summation k from 1 to n, and then we have J times xk plus D times uk. And so L is a summation, and here we have integer coefficients multiplied by the x's. This is not surprising because, as I said, because the x's are coprime, then in fact every integer, not just positive integer, can be written as an integer combination of the x's. But now we are interested in the integers that can be written as strictly positive combinations, integer combinations of the x's. So I want the L to be expressed as a summation of coefficients times the x's and all those guys so needed that those are greater than or equal to 1. The idea is, if L is large enough, then this is possible. So if L is large enough, then we can write down L as a strictly positive integer combination of the x's. In other words, that L will be, a sum of coefficients times the x's, and the coefficients will be strictly positive. To show this, just choose L to be greater than or equal to this quantity here. So this quantity is this integer that is the sum of the x's squared times 1 plus the maximum of the negative of the integer coefficients that are used to express the GCD, which here is equal to 1. As I said above, that basically one of those u's is non-positive, and so so there exists uj such that uj is less than or equal to 0. So there is a j such that minus uj is greater than or equal to 0. One of those elements is greater than or equal to 0, and so this means that this maximum here is greater than or equal to 0. Okay, now let's focus on the quotient. So what will happen when you divide L by the summation? The quotient is J. It is the floor of L over the summation, and the floor of any real number is greater than or equal to the real number minus 1. Now our L is greater than or equal to this quantity. So if we divide by the summation and then subtract 1, then it means that J is greater than or equal to L over the sum minus 1, which is greater than or equal to the sum itself times this bracket containing 1 plus the maximum of minus u1, minus u2, and so on. And then there is this minus 1 here. So this will be J, the quotient, the floor of L divided by the sum. Now, take this summation multiplied by 1 and then subtract 1. So we get this term. Now, small n is an integer greater than or equal to 2. And then we have those guys, those x's are distinct positive integers. So basically, the smallest possible value of this summation is, 3, right? So, 2 terms, one of them is 1 and the other is 2. So we have 3 minus 1, that's 2. So basically, this is greater than 1. This term here is greater than 1. What about the other term? Well, the remainder of division is inferior to the summation, right? So this summation here is greater than the remainder of division. And then the maximum of those terms, minus u1, minus u2, all the way to minus un, is greater than or equal to any of them. So this maximum is greater than or equal to minus uk for every k, in the set 1 to all the way to n. Okay, so if we choose big L to be so think of this as like a threshold, and we choose L to be equal to this quantity or more, what will happen? What will happen is that the quotient of division, which is J, will be superior to 1 plus D times UK for every K. So J is greater than or equal to 1 minus DUK. Move this term to the other side. So J plus DUK is greater than or equal to 1. So in this case, those coefficients here will all be strictly positive integers. Okay, so this is the idea that if L is a large enough strictly positive integer, we can write it not just as an integer combination of the x's, but as a strictly positive integer combination of the x's.